in our Fock space, we have somehow lifted the vector space H to having n copies of H, and also letting n open. And so we have somehow a tensor product of the Hilbert spaces, but usually in Hilbert spaces we are really interested on operators on the Hilbert spaces. And yeah, there of course are also tensor products for operators. So if we have operators in the underlying Hilbert space H, we can also lift this in canonical ways to the tensor powers. And that's what I want to do in the next remark. And that is something which is connected with this notion of second quantization. But let me first start with defining the relevant notions. So I'm looking on the Fock space over this underlying Hilbert space H, and now assume I have an operator, and let us do it for bounded operators. Let us assume T is a bounded operator on H, and then I'm claiming that we can define also a tensor product, a tensor power version of this T, which acts on H to the n. And this is defined in a maybe canonical way, that actually if I'm acting on these elementary tensors, where I have x1 tensor up to xn, then I'm just acting on each component separately. So this is defined again by linear extension, because I'm only writing down the formula for elementary tensors, and general elements are given by taking linear combinations and then also going to a limit. But all this goes nicely through. So essentially I have to say what is T tensor n acting on x1 tensor xn. So the x's here are elements in my Hilbert space, which means this here is a basic component of a vector in H to the n. So I should say, how does this act here? And of course, I mean, you see the notation suggests, I think, that clearly this should act, that the T acts on this, on this, on this, and so on. So I just act on each of the x's separately. I have T of x1 tensor, T of x2 tensor, T of xn. And of course I can do the same, of course, if I have here the tensor product of different Hilbert spaces. Yeah, so this is the lifting of an operator from the base Hilbert space H to the H tensor n. But of course what we want is not to look on H to the n, but only on the symmetric subspace. But it should be clear from this representation here that this here is kind of symmetric. So if I start with something symmetric here, what I get here should also be symmetric, because all the factors are treated here in the same way. And this of course relies, so formally, maybe let me give the argument. This definition here commutes essentially with our projection operator onto the symmetric functions, and the projection operator is given by the u sigmas. So essentially we should just see that this T commutes with the u sigmas. So namely, and that's of course clear. So if I apply u sigma to T to the n, this is the same as applying T to the n to u sigma for all sigma in Sn. So this means if I'm applying T to the n first and then commute here my factors, or if I first commute here the factors and then applying T to the n, this doesn't make a difference, which should be clear from this definition here. So this means we have this, and this then will tell us that if I apply T to the n to a symmetric vector, or to a symmetric tensor, I still get a symmetric one. Okay, and so which means we should see that T to the n x, if x is symmetric, is in the range of P. So let us check this. So let me take an x in the symmetric part of the tensor power, so in H plus to the n, which means by definition that Pn of x is equal to x. Because this part was defined as the range of Pn acting on the h to the power n. Yeah, so let us take such an x, and now let us see what happens if I apply t to the n x to this. So then we know that this here is equivalent with the fact that the x doesn't change if I apply any u sigma. So this here I can also write as t to the n, and this x I can write as a u sigma x for any permutation sigma, because we know that's what we saw before, that this here is the same as that u sigma x is equal to x for all u sigma. Yeah, but now, because as what I said before, this here I can exchange, so this is u sigma t to the power n, and then you see that what I have here is actually now u sigma applied to, maybe let me write it like this, t to the power n of x. And so this tells me that t to the power nx is also a vector which is invariant under u sigma for all u sigmas, for all sigmas in the permutation group. But being invariant under u sigma for all sigmas is the same as being in a range of Pn. So this here implies, because I know this for all sigma, implies that Pn of t to the power n of x is actually t to the power n of x. So x is actually an element in the symmetric tensor power if x is there. So this means if I'm restricting, I can restrict t to the power n to the symmetric tensors, because it maps the symmetric tensors to itself. So that's the conclusion, what I want to get from here. So this means that the t to the power n I can also consider as an operator on the part of the tensor power in which we are really interested, so namely on this h plus to the power n. This is really, if I'm acting with t to the n on this, I'm really not leaving this space, so I can restrict t to this. And then maybe I give a specific name to this, and we can put, I mean, this is something which I'm constructing out of t, so I denote this by gamma. Gamma is the just notation for what I'm doing. I'm restricting to the plus space. I'm doing it here on the nth level, and it's something which I'm doing with t. And what is it, what I'm doing with t? This is just taking t to the power n, but restricting it to the symmetric subspace of h to the power n. Yeah, okay, so this is a nice construction. So if I have an operator in my underlying base space H, I can lift this with this construction to an operator on the nth, on the symmetric nth tensor power of H. Yeah, and of course this behaves very nicely in the argument T. So maybe I just write down a few properties. So first of all, for example, if I'm lifting the identity operator on H, I get, of course, the identity operator on the nth tensor power, which of course is clear from this definition. Then this is also compatible with taking the adjoint. So if I'm taking an operator T, lift it to the symmetric tensor power, and then taking the adjoint on this level, then this is the same as taking the adjoint of the operator T on the level of the operator H. Yeah, and also if I'm taking a product, this also fits very nicely. Maybe it's clear from this. If I have here t to the n, s to the n, this means that I'm just taking s times t n times. And also this respects the symmetric part. So I really have that if I take this construction for a product of operators, this is compatible. So I can take the product first on the base level and then lift it, or I can lift each of them and then take the product. So this means this is the same as gamma plus of n s times gamma plus n of t. Yeah, but one should know that of course this is not compatible with the sum. So I mean, if I'm taking sum t plus s here, then of course I will get mixed terms here. So I'm doing here a product construction, a tensor product construction. Of course, this should be compatible with the product, but the sum doesn't fit with this. So one should be careful. The sum, of course, is not really respected by this. So in general, of course, we have that gamma plus n of the sum of two operators is not the same as the sum of the operators after lifting. So gamma n of s plus gamma n of t. Yeah, and then maybe it's also interesting about the norm. How does the norm behave? And I mean, this is in particular interesting to see how this behaves in n, because, as you probably can guess, I'm not so much interested in doing this just for one fixed n, but in the end I want to do this for all n, because my bosonic Fock space, of course, is the direct sum of all nth powers, so I should then also act with my operator t to the power n on each of these n's. And of course, the point is, if I'm starting here with a bounded operator, it would be nice to have also a bounded operator on the Fock space, and for this we should also be able to control somehow the norm. But you see already here, if I have here the norm of this guy, should probably be the product of the norms of t. And if t has a norm which is bigger than 1, then this will explode in n. So this means we should restrict to operators which have norm less or equal to 1, so-called contractions, because then I can define this also as a bounded operator on all. Of course, we can deal with unbounded operators, so it's not, I mean, if we don't have a contraction, we start with a bounded operator, we still could lift it as an unbounded operator to all, to Fock space, but here maybe it's I'm looking on a nicest situation, and for this we should first know really what is the norm of this lifting of t to the nth power, and this is really, as should be obvious, from this t to the power n. Yeah, okay, but maybe, I mean this, because we also have to look on linear combinations of such guys, it's feasible that it should be like this, but maybe it's not totally obvious, so maybe in exercise we can really do the details for this, but at least that's really the result which is true, and this tells me that if the norm of t is less or equal to 1, then the norm of this lifting of t to the nth level is, this norm is bounded, even if I make n arbitrarily large. So thus the norm of gamma n of t stays actually bounded for all n if and only if the norm of t is less or equal to 1. So if the norm of t is less or equal to 1. Yeah, but this means if I have a contraction operator t on the Hilbert space H with norm less or equal to 1, then I can define those guys for each n, and then of course I can take them all together, and this gives me then an operator on the symmetric Fock space. And this operator is what is usually called the second quantization. So let me define this here. This is what we now really want to do here. Namely, not just lifting it to n, but lifting it to the whole Fock space, which is the direct sum of all n's. So I'm starting with an operator, a bounded operator in H, but actually not any bounded operator, but I require more, namely it should be a contraction which means that its norm is less or equal to 1. Yeah, and then I can define this gamma plus of t now for all n. And then I'm just calling it gamma plus of t. So then, and that's what I then really call the second quantization. And because I'm on the symmetric Fock space, maybe the symmetric second quantization. So then, but because we are only dealing with the symmetric situation, I mean, I'm not always using this because it's clear, so symmetric second quantization so I denote this by gamma plus of t. So this is defined as, so it's gamma plus of t. So this is now the direct sum of those operators, gamma t of n, gamma plus n of t, where n is running from 0 to infinity. And this is now a bounded operator on the symmetric Fock space of H. And of course, this direct sum here means that if I'm having a vector, maybe I should really say maybe explicitly what this means. So elements in my full Fock space, so let me call them x0, x1, x2, and so on. That's element in my Fock space, and they are mapped to applying the corresponding gamma n of t to the corresponding component. So I'm taking gamma plus 0 of t acting on x0, gamma plus 1 of t acting on x1, gamma plus 2 of t acting on x2, and so on. And this gives me a new element in the symmetric Fock space. Yeah, and of course the question is, I mean, what is gamma 0 of t? I mean, x0 is just a complex number, so this complex number has nothing to do with h, so it doesn't see anything of t, and of course there I'm just taking the identity operator. So this guy here, so t, so in the same way as h, yeah, maybe, so if I have a Hilbert space and I'm taking the zeros tensor power, this is just C. So I'm losing, essentially, I'm losing all information about my Hilbert space. And if I'm taking this t to the power 0, that's the guy which should act here. This, of course, is just the identity operator on C. So again, I'm losing all information about my operator t. Yeah. Good. Okay, so that's the second quantization. And maybe if you wonder what does second quantization mean? I mean, first of all, what is quantization and why is it the second quantization? So quantization usually means this transition from classical physics to quantum physics, that we are replacing the quantities, momentum, position, which we have in classical physics, and which are given there by functions or commuting commuting things, that we replace them by things which don't commute. That's the quantization. We go over to operators which don't commute. P and Q don't commute anymore. In the classical context, of course, those guys are just commuting objects. But quantization means we consider non-commuting objects of this. And now the second quantization is now that, so this, maybe you might think of, that happens on this Hilbert space. So this underlying Hilbert space H is the first quantization, because that's how you describe, let's say, one particle. And now the second quantization tells you how you get from one particle to an arbitrary number of particles. And this is just given by lifting the structure of your operators, which you have in H, to all those tensor powers. And this is a very precisely defined procedure. And so there is this very nice saying by Ed Nelson that first quantization is a mystery, but second quantization is a functor. Functor. So it's a very well-defined mathematical object, and functor means it has, so it's something which depends on T, and it has very nice properties in T. So all the properties, or most of the properties which you have on the underlying Hilbert space are going over in a functorial way to these liftings. So this means, I mean, first quantization, this is very hard to say what this really is. So how, if you have a classical system, how do you go over to the corresponding quantum system? Well, of course, physicists have a lot of ideas and know essentially how to do it, but it's very hard to say this mathematically precisely. But second quantization, just going from the Hilbert space H to the Fock spaces over H, this is mathematically very clearly defined. So there is no problem with this.